Right, let's get started. So today we're going to discuss inverse reinforcement learning, continuing from our discussion of control as inference from last week. So today we're going, so far all the reinforcement learning algorithms that we've discussed have this kind of paradigm where you manually design the reward function to define the task. And we basically saw essentially two ways to get control policies: directly imitating demonstrated behavior and manually designing reward functions. And today we're going to see something that kind of, in a sense, puts the two ideas together, using demonstrated behavior to learn reward functions. So the idea in inverse reinforcement learning is that you learn the reward function from serving an expert, and then once you have that reward function, you can use regular reinforcement learning to re-optimize it in new settings to get behavior that, in principle, the expert would have done. And we'll talk about how this compares to the regular kind of imitation learning that we saw before. So the way that we will actually derive algorithms for inverse reinforcement learning will actually be by applying the approximate optimality model from last Wednesday. So the goals will be to understand the inverse reinforcement learning problem definition, understand how probabilistic models of behavior can be used to derive inverse RL algorithms, and understand a few practical inverse RL algorithms that we can actually use. So in the first half of today's lecture, I'm going to describe the basic mathematical framework and arrive at a method that is mathematically sound but not terribly useful in high-dimensional spaces. And then after the break, I'll talk about how to actually instantiate sort of the deep RL analog of inverse reinforcement learning. All right. So last week, one of the things we talked about is this idea that maybe besides reinforcement learning just being a useful way to acquire policies, it can also maybe be a useful way to model the behavior of other intelligent and rational agents like human beings. And we talked about how there's a long history in biomechanics and psychology and so on and neuroscience of using models of optimality as a way to describe how rational agents like humans behave. And we talked about how a very reasonable way to approach this would be to say, well, we've got these nice optimization problems that we've set up before. These optimization problems describe what actions a rational agent should take if that agent is trying to maximize its reward. So if we observe the behavior of, let's say, a person or an animal, then perhaps we can infer their intention by essentially inverting this sort of optimization process by asking the question, what kind of reward function can we plug in here such that the solution to this maximization corresponds to the sequence of actions that we actually saw from the human or animal. And then one of the issues that we talked about that starts to come up once you start thinking in this way is that traditional models of optimality basically yield one optimal behavior. So if you have a deterministic environment, you will get a deterministic policy, and that deterministic policy will do the perfect, most optimal thing. And when we actually observe the behavior of humans and animals in the real world, they don't actually do exactly the same thing every time, and they don't seem to do the perfectly optimal thing every time. They sort of trade off their optimality in such a way as to get the really important stuff right, but behave in seemingly arbitrary ways for the stuff that doesn't seem so important. And we discussed a probabilistic model that allows us to describe this sort of soft or approximate notion of optimality. So today we're going to talk about using this model to learn rewards. And before I do that, what I'm going to do is discuss a little bit about why we want to learn reward functions, talk about some older methods for inverse reinforcement learning that sort of predate this probabilistic model of soft optimality, and then spend the rest of the lecture discussing how we can apply the graphical model view of control from last week to inverse RL. So let's start with a little bit of motivation first. So why should we worry about learning rewards? There are kind of two perspectives we can take on this. There's an imitation learning perspective and a reinforcement learning perspective, depending on which of these two things you're more concerned about. So if you are a big fan of imitation learning, then you could imagine that maybe the way that we learn to do imitation learning so far has a few issues with it. So the standard kind of imitation learning view, the kind that we've covered in the beginning of the course, takes this sort of standpoint that a demonstration that you're imitating is provided directly through the embodiment of the system that you're trying to control. So if you wanted to drive a car, you need examples of states and actions of someone actually driving the car. So you copy the actions performed by the expert. So this if this robot is being taught by imitation learning, it's not going to learn by watching a person pick up a cup and put it on the plate or something. It's going to learn by having a person actually move the robot through that motion so that it can see both the states and the actions that it's supposed to take. That is not an entirely unnatural way to think about imitation learning, but it's sort of only a very small subset of what people actually do when we imitate. We can imitate by somebody actually guiding our body through some motion, but typically we do it by observing what somebody else did. And the standard view of imitation learning that we discussed earlier in the course doesn't really have any ability to reason about outcomes of actions. So the autonomous car that we saw that was trained with imitation learning, that model wasn't trying to figure out, well, if I turn the steering wheel like this, I will stay on the road, and staying on the road is good because that's what the person did. No, the car is just, the model for driving the car is just saying, well, the person took this action, so I'll take kind of a similar looking action. So it's a very greedy view of imitation. If we look by comparison at what people do when they imitate other people, you see something a little different. So for humans, imitation learning is really more about copying the intent of the demonstrator, not necessarily their particular actions. And this sometimes leads to some interesting outcomes, like we'll see in a second. So you might actually take very different actions than what the expert took. So this is a video that I actually showed in the first lecture of the course. This is a psychology experiment. This guy is not even really demonstrating something, but clearly they're trying to accomplish some end goal. And this is the experimental subject. He looks at what this guy is doing and figures out, well, actually, the best way to accomplish this goal is to carry out very different actions. So in terms of the physical motion of the body, he's doing something completely distinct, but in a way that brings about the demonstrated intention. OK, so maybe that suggests that there's a lot of room for improvement relative to the classic kind of imitation learning view that we saw in the beginning of the course. Now, that's if what you care about is doing a better job of imitation learning. Maybe what you care about is doing a better job of reinforcement learning. So you don't really care so much about who we're imitating or why. You just care about the end result. Can we get an autonomous agent to do something sophisticated and useful in the world? So far, whenever we talked about reinforcement learning algorithms, we just sort of assumed that we were in a setting where defining the reward function was pretty straightforward, and we didn't really need to figure out how that happened. So, for example, for the Atari games that you guys have hopefully all trained your Q-learning agents on. If you haven't, you should do that. But you might not have enough time to train them before midnight, but hopefully you've all done that. For those Atari agents, their reward function was pretty obvious, right? So the game has a score. The score is right there on the screen, so it's pretty obvious that that's the reward function that you should use. But in the real world, things are often not quite so simple. So if you do actually want to drive the autonomous car on the freeway, well, you might say maybe your reward function is something simple like get the car to its destination, but that clearly doesn't tell the whole story. So you want to get the car to its destination, keep the passenger comfortable, obey the traffic laws, also obey some unstated social conventions, like maybe it's not strictly illegal to do some things, but considered extremely impolite. So there's a whole host of complicated factors that you have to take into account that are not part of the learning process for the policy, but they're actually part of the task specification, part of the reward specification. So perhaps it would be much easier and much less manually demanding to define objective functions for a task like this by instead demonstrating good driving behavior and having an algorithm automatically figure out from that good driving behavior what an appropriate reward function would be. Of course, it's somewhat situational, so in some tasks like the Atari games, it's much, much easier to just say, this is the number that you're trying to maximize, but in some other tasks, it's a lot easier to show the machine what you want it to do than to write down a reward function. Okay, so the inverse reinforcement learning problem deals with the problem of inferring reward functions from demonstrations. So you show some behavior that you believe adequately illustrates the intent that you'd like the agent to accomplish. And then from that, you get a reward function, R of S comma A. And then once you've got that, then you can use any of the reinforcement learning algorithms we've covered so far to maximize that reward function. Now, there are a few pretty major issues with doing this. One major issue is that by itself, this is an underspecified problem. So if I just say, here's a demonstration. This demonstration came from a policy that was optimal or close to optimal with respect to this unknown reward function. Give me a reward function that will produce this outcome. There are actually many, many answers that, without any additional statement about this problem setting, seem equally good. So here is a little grid world. It's a little 4x4 grid world with 16 states. And let's say that I demonstrated this behavior. So go right 3 steps and then down 1 step. So if I demonstrated this behavior, you might think, well, okay, what's a reward function that explains this? And there are a few explanations I can come up with, and these explanations are all going to be equally good. So for example, I might say, well, my reward function is very low everywhere, but it's pretty high in this one square, so that's why that trajectory goes in that direction. That seems pretty reasonable. I might also say, well, my time horizon is exactly 4, and this was actually my reward function. That's actually kind of equally reasonable. Or you might say, well, maybe this is my reward function. Like maybe all you want to do is get to the bottom half of the grid, but there's like a little wall here, a little region of low reward, and you don't want to pass through that. That's why you went to the right. So they're all different explanations for the same thing, and under suitable assumptions, they might all be equally good. In fact, you might get even more ridiculous explanations if you have rewards that depend on states and actions. You could also have a really trivial explanation, which is that actually the state doesn't matter. All that matters is that over here you get a reward of plus 1 million for going right and minus 1 million for everything else. Same here, and here it's plus 1 million for going down. So kind of a silly reward function that just tells you, like, take exactly the same action that you saw the demonstrator take. And these explanations are all equally good unless we bring in some other kind of criteria or some other kind of constraints on the problem into the picture. And that's actually what our probabilistic model is going to do. But first, let's try to set up the problem setting a little more formally and talk about how people approach the inverse RL problem in the past. So a bit more formally, what I'm going to do is I'm going to write down the assumptions of the forward reinforcement learning problem on the left side and the inverse reinforcement learning problem on the right side. So in both cases, we assume we have some kind of state space and some action space. So we're going to have essentially an MDP definition on the left-hand side. On the right-hand side, it's going to be an MDP without rewards. So that means that sometimes you know the transition, sometimes you don't, and you just are allowed to sample from them. So that determines whether you're doing like the model-free RL thing or something more like dynamic programming. And then for forward RL, you're also given a reward function, which fully defines your MDP. For inverse RL, you're not given the reward function. So in forward RL, you take the reward and you learn your optimal policy. In inverse RL, you assume that you observe samples, sample trajectories, that were produced by an optimal or near optimal policy, and then learn a reward function. And I'm going to use the subscript psi to denote the parameters of the reward. So I've used theta for the parameters of the policy, phi for the parameters of the value function. So I'll use psi for the parameters of the reward function. And then, of course, you need to choose a representation for your reward function. And there are a number of different representations that people have used in the past. So one very popular choice that was used in some older work in inverse RL is to use a linear reward function. So you can think of the parameter psi as being weights on a set of features. And intuitively, these features are basically things you want or don't want. So for your autonomous car, maybe it has a feature for, am I currently colliding with another vehicle? Am I currently in a lane? Am I currently at my destination, etc.? And those are all things that you either want or don't want. So you put a positive coefficient on the things you want and a negative coefficient on the things you don't want. That's a very simple representation for a reward function, and there are some simple kind of provably convergent algorithms we can derive that use these linear representations. But you can also have a more expressive representation, and we'll also talk about how you can learn fully unconstrained kind of neural net-based reward functions as well. So here the parameters would just be the weights in the neural net. It would take in the state and the action and output the reward function, the scalar value. And of course, once you have the reward function, then you can use it to learn the optimal policy pi star. And if you've recovered the right reward function, you can learn that policy in new settings other than just the one in which the demonstrations were provided. Okay, does anybody have any questions about the definition of the inverse reinforcement learning problem? Okay. All right, so what I'm going to do next is I'll briefly describe a few algorithms for inverse RL. I won't cover them in enough detail for you to actually quite implement them. This is almost kind of more to give you a little bit of context about what some earlier work in this field tried to do. And then the bulk of the lecture will be spent on what's called maximum entropy inverse RL, which uses the probabilistic models that we derived last week. But before we get into that, we can think of some maybe simpler ways to approach the inverse RL problem. So let's stay away from the neural net view of things for a second. I'll just focus on this linear function approximator view. So I mentioned that a very simple way to represent your reward function is as a linear combination of features where each feature is either something you want or something you don't want. So at that point we could say, well, maybe a good choice for these weights psi is a choice that results in the optimal policy corresponding to the learned reward having the same feature expectations as the demonstrations. So if the features are the things that are important, what if we disregard everything else, just pay attention to the features and say, find me a reward such that its optimal policy has the same feature expectations as the demonstrations. This seems kind of reasonable because you could surmise, well, if this particular feature has an expected value of 37, if I'm also getting an expected value of 37, I probably found a reward that results in a behavior that matches the demonstrator, at least in regard to those features that you gave me, which are presumably the things that you care about. So if your car collided 0 times and stayed in the right lane 97% of the time, and you produce a reward function that also collides 0 times and stays in the right lane 97% of the time, maybe you found a reward function that actually matches the intent of the demonstrator. So we can write this down formally by saying that pi superscript r psi is the optimal policy for the reward r psi. And then we can just write it like this. Pick psi such that the expected value under pi r psi of the features fsa is equal to the expected value under the optimal policy, that's the policy from the demonstrator, pi star of fsa. Okay, so actually finding r psi is rather involved, but let's start with a simpler question. If you have a reward function r psi, how can you evaluate the left-hand side and the right-hand side of this equation? Any ideas? Let's start with the right-hand side, because that one is a little simpler. So pi star is the unknown policy of the expert, of the demonstrator. So our assumption in our problem statement is that we observe samples from pi star. So that's what our demonstrations are. Our demonstrations are samples executed by an expert who is performing actions according to this unknown pi star. So how can we evaluate the right-hand side of this equation? Yes? Right, so the answer was, well, just take your samples. For each of your samples, sum together the features, and then divide by the number of samples. Right, so you can estimate this right-hand side of this equation just by using your samples to essentially calculate the expected value approximately. What about the left-hand side of this equation? Well, it's a little bit of a trick question. It depends a bit on how you're actually trying to solve this problem. If you only have access to the dynamics via sampling, which was a standard assumption model free RL, then maybe you run an entire reinforcement learning algorithm to learn pi r psi, like basically take one of the algorithms from before, just run it all the way to convergence, and then run that policy a bunch more to generate a bunch more samples, and then use those samples to estimate the left-hand side. That sounds like kind of a huge pain, but it will do the job. Okay, so that's kind of one option. You use samples for the right-hand side, somehow produce samples for the left-hand side. So if you only have r psi, you need to actually learn pi r psi using RL, then generate more samples. If you actually know the dynamics of the system, then you can actually use a dynamic programming algorithm to figure out the left-hand side. So you can run something like value iteration, you get a complete value function for your reward function, and then you calculate your visitation frequencies for all your states and sum that together. That's intractable in high dimensions, but in low dimensional spaces with known dynamics, that's also something you could do. Okay, so the expectation on the left-hand side is under the state action marginal under pi r psi, but of course you get samples from the state action marginal by taking samples from your trajectory distribution and then just summing over all the time steps. That's totally fine. The right-hand side is under your unknown optimal policy, which you approximate using the samples from that unknown optimal policy, which is exactly what your demonstrations are. Now, this is still an ambiguous formulation. There might actually be multiple policies that match the feature expectations of the expert. So when people started thinking about this problem in the early 2000s, this was around the time when a very popular way of solving classification problems was something called support vector machines. So people thought, well, can we apply some ideas from support vector machines to inverse reinforcement learning? In support vector machines, there's sort of a similar conundrum that comes up if you have two different classes and you want to draw a decision boundary between those classes. Many decision boundaries might separate the classes perfectly, so the question is which one you pick, and the somewhat arbitrary but mathematically perhaps interesting answer is pick the boundary with the largest margin. So people thought, well, can we apply that principle here too? Can we pick the reward function that in some sense draws the largest margin between the policy of the expert and all other policies? So the idea was, let's find the parameters psi so as to maximize a margin, where the margin is basically given by the largest number that you can add to the reward. So this is just the expression for our psi, to the reward of any other policy besides the optimal one. So this is an equivalent of saying, I want to find psi such that the optimal policy is better than all other policies with respect to r psi by at least my margin m. Okay, some of you might be looking at this and thinking this is a little bit bizarre. Does anybody have any thoughts about what's strange and peculiar about this? Yes?
Seems a bit strange, like, if your policies could, like, be very close together, like, exactly the same, except, like, your policies, like, a little bit different, like, their expectations are probably almost the same.
Right, so the comment was, it seems a little weird because you could have other policies other than pi star, that are very close to pi star, and you're asking them all to have this margin m. So in particular, maybe, remember policies can be stochastic, so maybe pi star takes an action with probability, 99%. Now you have another policy that takes it with 98.99999%, and you're asking that to have a margin of m. So that kind of doesn't really make sense. So of course, what you have to do in order for this to make sense is to have the margins scale with the difference between the policies. And the way that people thought about approaching this is to first apply the everyone's favorite SVM trick. So the SVM trick takes this original max margin formulation and uses the dual to turn into something like this. So instead of maximizing m, you just minimize the squared norm of the weights. This is basically exactly what you all probably saw in your machine learning class for SVMs. This is the problem that we typically solve, not that top one. So now you're minimizing the norm of the weights, and your margin turns into 1. And then from here, it's much easier to bring in a notion of similarity between policies. All you do is say, well, instead of enforcing a margin of 1 against all other policies, you enforce a margin that increases as the dissimilarity between the policies increases. So this is some measure of difference between two policies, and there are many different choices you could make here. So if pi is the same as pi star, then the margin is 0. If pi is very, very different than pi star, then the margin will be large. And for anything in between, the margin scales. So if you have that policy with probability 0.9899999, it'll have a small divergence, and therefore it'll demand a relatively small margin. So this actually makes it possible to operationalize this idea into an algorithm that actually makes sense. One choice you could make for this divergence is actually the difference in feature expectations, which is convenient because then you can actually write out this whole inequality purely in terms of feature expectations. Now, there are still a few issues with this formulation. So this formulation will give you an inverse RL algorithm, and there are methods like maximum margin planning that actually instantiate this idea in a practical framework that can be solved with quadratic programming and can even be used with sample-based estimates. The issues are that, first, maximizing the margin is a little bit arbitrary. It does give you a kind of a tie-breaking rule, so it does disambiguate different solutions. But it's not clear whether this tie-breaking rule actually makes sense from the standpoint of the problem that you're actually trying to solve. So you will get a unique optimum if you set this up properly, but that unique optimum might not actually be the one that's most preferable. So it's not clear what forward model corresponds to this particular inverse RL method, meaning what notion of for what notion of optimality is this reward the best one. There's not really a clear model of expert suboptimality. So all of this is derived from the assumption that the demonstrations were in fact produced by the optimal policy, and if that is not the case, then this doesn't really make sense. The way that people approached it in the past is the same way that they approached the fact that your data set may not be linearly separable for an SVM, which is by adding slack variables. So in an SVM, you say, well, you want the largest margin, but then you add some slack variables and you try to minimize those slack variables, and you can do that for inverse RL as well. And then the other problem is that you end up with a kind of a messy, constrained optimization if you go this route, which is fine for linear reward functions, because then you can set everything up as a QP and use widely available QP solvers, but it's not a great fit for deep learning. So if you have, for example, a nonlinear neural net representation of your reward, it's very hard to make a trick like this actually workable. However, if you do want to learn more about this sort of max margin view of inverse RL, I would recommend these two papers for further reading. So this paper by Beal and Ng called Apprenticeship Learning via Inverse Reinforcement Learning was arguably the first practically usable inverse RL algorithm. And this paper by Ratliff et al. Called Max Margin Planning is probably one of the more sophisticated, more modern reformulations of this margin-based setup that actually works in practice. I'm not going to talk any more about this because I think that you can actually do a much better job of inverse RL if you bring in a notion of essentially of probability theory, a notion of uncertainty about the behavior of the expert, and that's what we're going to do next. So remember the issue that we raised before about the optimal control view of modeling behavior, that while it gives you a explanation for why somebody might do something, it doesn't by itself explain why they might do things that are a little bit suboptimal. So last week we discussed that we can instead formulate a probabilistic model to describe near optimal behavior. In this probabilistic model we have, we basically draw this graphical model. Our conditional probability distributions are the initial state distribution P of S1, the transition probabilities P of ST plus 1 given ST AT, and the important one, the probability of optimality, which we defined to be the probability of a binary random variable whose probability of being true is equal to the exponential of the reward. This requires a small regularity condition, which is that the reward should always be negative. In practice, you actually don't need this, and you can handle it fine with positive rewards as well. But for the theoretical derivation, let's just assume they're always negative and not worry about that. So we saw how if you take this model and you compute the posterior, the probability of seeing a trajectory, given that the optimality variables are true at all time steps, you actually get a model of soft or approximate optimality, meaning that suboptimal trajectories have a non-zero probability of occurring, although more optimal trajectories are more likely. So this is just a quick recap of what we saw last week. I can draw the graphical model of just states and actions, and I can ask the question, what's the probability of a sequence of states and actions? But that just tells me what's the probability of them occurring physically, like are they physically plausible or not? So physically impossible things have a probability of 0, and so on. So this is not really quite what I was interested in. And then to get a model that actually describes optimal or near optimal behavior, what I did last week is I added these optimality variables, and now I can ask the question, what's P of tau given O1 through t, where OT given SDAT is this exponential R. And then you apply, definition of conditional distribution, crunch through this whole thing, and you end up with this equation, that it's the probability of the trajectory occurring via physics, like P of tau, times the exponential of the total reward. And we saw how this has like a very nice intuitive interpretation. So the most optimal trajectory is the most likely. As they become suboptimal, they become exponentially less likely. And we could set up these nice backward and forward recursive algorithms to actually calculate these probabilities in a reasonably tractable way. Okay, but today what we're concerned with is not actually finding p of tau given O1 through t. We already learned how to do that last week. Today what we're concerned with is finding the r. So we want to learn the optimality variable. So what we saw last week essentially amounts to inference in this graphical model. What we'll see today amounts to learning in this graphical model. Learning what? Well, learning r. Right? So I'm going to now write it as r subscript psi, the same psi that I mentioned before. So psi is the vector of parameters that describe your reward function. And your goal is to find that vector. Now we need to set up an objective. And fortunately, once we have everything cast into the framework of probabilistic graphical models, finding an objective is very easy. The objective is just going to be maximum likelihood. Okay, so we'd like to learn the reward parameters psi. So I'm going to, just to make this explicit, I'll always write p of ot given stat comma psi, just to emphasize that this depends on psi. Psi is not a random variable here, it's just a deterministic vector, but I'll write it like this anyway, just so that you don't forget. And as we saw before, the probability of a trajectory given optimality is p of tau times the exponential of the sum of rewards. And the trajectories are exactly what you're given. So your data consists of the trajectories that were taken by the expert. So this is the probability that you're going to try to maximize with respect to psi. So you're given samples, tau I, sampled from pi star of tau. So your maximum likelihood objective is just to maximize, with respect to psi, the sum over all of your example trajectories of log p of tau I given O1 through t, comma psi. And if you can solve this optimization problem, then you will have acquired the parameter psi that assign the highest likelihood to the demonstrated trajectories, and therefore give you the right reward function. Okay, does anybody have any questions about this problem setup? Okay. All right, so if we're talking about optimizing this with respect to psi, we can actually ignore this, this physics term here, because changing the reward function isn't going to change how physics works. So all we really care about is that exponential of total reward term. So obviously the way we're going to do this is we're going to calculate a gradient through this thing, so this first part doesn't really affect us. So what we can do is we can substitute it in, this log p, treating the p of tau part as a constant, and what we're going to get is the log of the exponential of the total reward, which is just the reward of the trajectory, minus this log z. What is this log z? Well, this log z is the thing that causes this stuff to sum up to 1. As a quick check of everybody's understanding, the probabilities need to sum up to 1 with respect to which variable? You can just shout it out. Louder? I heard somebody say the right answer. All right, so let's work through this, because I think this is important. This is our likelihood. So this is our log likelihood, log p of tau. We're going to substitute in this bit. That's unnormalized because we have this proportionality sign here. So we substitute in the log of the exponential of total reward. That gives us the reward of tau. Now we can't just maximize the reward of tau, because we have to account for the fact that this is a probability distribution. So a probability distribution sums up to 1. It sums up to 1 with respect to which variable? Tau. Thank you. OK, so that means that z is the integral over all possible trajectories tau of r psi tau. OK, and this is the hard part, because let me tell you, there are quite a few trajectories. And summing over all of them can take a very, very long time. In fact, it can take an exponentially long amount of time, which means we don't want to do that. So let's talk about this partition function. Because if it wasn't for the partition function, this would all be really easy. You would just say, just take the trajectories you saw in the data, make the reward values be as large as possible, ideally infinity, because that's the biggest number you can find, and just call that a day. But of course, that's not a very good explanation. So z is given by the integral over all trajectories of the probability of that trajectory times the exponential reward. So this is just the same thing I had on the previous slide, but now integrated over all trajectories. And this intuitively makes sense. This is just saying, well, if you want to find the right reward function, make the reward function of the observed trajectories be big, but at the same time, just making the numbers bigger isn't enough. You have to make it bigger than the rewards of other trajectories. So that's what that partition function does. It basically says, don't just make the numbers big, make them big relative to the other trajectories that you didn't see. If you can do that, then you know that you found the right reward function. But of course, those other trajectories that you didn't see, you have to only consider the ones that are actually possible. So you could say, well, okay, the car driving down the road is good, the car flying to the moon is not good. But that's not really useful because cars can't fly to the moon. So what you want to do is find all the physically plausible trajectories that the expert didn't execute, not the trajectories that didn't happen because they're impossible. Okay, so let me take this definition of z and plug that in there. So when I plug in the definition of z, what I'm going to do is I'm going to actually calculate its derivative. So I've kind of skipped a step here. Take that, plug that in there, and then calculate its derivative. Now when you take the derivative of a log, you get 1 over that number. So that's where I get the 1 over z term. And then in the numerator, I just get the derivative of the integral. Now inside that integral, the only part that depends on psi is the exponential. So I get the same p of tau. And then the derivative of the exponential is just the exponential itself times the derivative of the stuff inside the exponential. So that's where I get the grad r psi. Take a moment to digest this equation because it actually reduces to something quite elegant. Some of you might have already noticed this, but essentially 1 over z times p tau exponential r is the probability of that trajectory. So this integral can be equivalently rewritten as an expectation of grad r psi. So this whole bit, everything except for the grad, is basically the probability of tau given O1 through t comma psi. So that means that that whole thing can be rewritten as the expectation under the soft optimal policy for my current reward of grad r psi. And then the first term is just a sample-based estimate of the expectation of the gradient under pi star. So now this is actually starting to look pretty convenient. We have the difference of two expectations. The first one taken under the optimal policy, the expert's policy. The second one taken under the optimal policy for our current reward. And inside both expectations, you have the gradient of the reward function. So that's kind of nice. That means that the gradient of this likelihood is basically going to point in the positive direction for the trajectories that come from the expert. So it'll increase the reward of the expert's trajectories, and it'll point in the negative direction for the samples from the policy corresponding to the current reward. So it'll say, make the expert's trajectories more rewarding, and make the trajectory sample from your current policy less rewarding. And of course, they'll cancel out to 0 when those two distributions are equal. So that's quite nice. That means that you will just keep making the expert's samples more rewarding, your own samples less rewarding, until the two distributions are the same, at which point this whole thing will cancel out. You get a gradient of 0, and then you're done. And of course, the first term is easy to estimate just by using the demonstration samples that we've got. So the complicated part is that second term. Okay, so you estimate the first part with expert samples, and the second one is an expectation of the soft optimal policy under the current reward function. So that's the bit that we're going to deal with. Okay, so let's talk about this expectation. In fact, pretty much the rest of today's lecture will be spent on talking about different ways to estimate that expectation. Because the first part, its expectation is easy. You just use your samples. It's really the second part that gives us trouble. So I'm using the shorthand r psi of tau, but don't let that confuse you. What that really means is the sum over the time steps of the reward at that time step. And what we can do is we can take that sum and we can take it all the way out of the expectation by linearity of expectations. And when we take it all the way out, then the expectation can actually be taken with respect to the state action marginal at that time step. So the whole expectation is over trajectories, but when the stuff inside the expectation only depends on the time step t, we can take it over just the state action marginal at time step t. Right? So now we have a sum over t of the expected value with respect to STAT of grad psi r psi ST-AT. And now we're going to look back to the material from last lecture to help us calculate these probabilities. So I'm going to use the chain rule to break them up into P of AT given ST, comma optimality, times P of ST given optimality. And these things we saw before. So the first term is simply our soft optimal policy. And we saw last week how if we have backward messages, we can actually calculate those probabilities using our backward messages. So does anybody remember the expression for that first term in terms of the backward messages? Anyone want to volunteer an answer? It involved a beta. All right, so the backward messages, if you remember, give us the probability of optimality at all the time steps in the future, given a current state or given a current state in action. So we had a beta t ST-AT and we had a beta t ST. And then we saw that if we take the ratio of beta t ST-AT and beta t ST, then there is this nice trick via Bayes' rule that we could use to recover exactly this expression. So the first expression is just the ratio of the backward messages from before. So this is basically the answer to question 2 from last Wednesday. So we run our dynamic programming procedure, calculate those backward messages beta, then take their ratio, and that gives us the probability of the action given the state and optimality. The only thing that's different now is that I have a psi in there, but the psi just parameterizes this thing, so it doesn't change the dynamic programming procedure. The other term, that one we saw at the end of question 3. So question 3 was how do you calculate the forward messages? And we saw that once we calculate both backward messages and forward messages, we could multiply them together to get the probability of a state marginal. The probability of being in a particular state at a particular point in time, given optimality at all time steps. So now if we multiply them together, the beta ST term cancels out, so you're just left with beta ST-AT times alpha ST. And this is up to a constant of proportionality, so you still have to normalize it with respect to states and actions, but otherwise this gives you the probability that you want. So you have a backward message, a forward message, multiply them together, get a probability of a state action tuple. Now, all of this is making some pretty egregious assumptions so far, and those assumptions will be relaxed in the second half of the lecture. The egregious assumption, of course, is that you can enumerate all states and actions, actually calculate these messages, multiply them all together, and even worse, after that, normalize them, so that this isn't just proportional, but actually equal to. So that, of course, requires your state space and action space to be small enough that you can go through every single state and every single action. Now, that is still not nearly as bad as going through every single trajectory, because the number of possible trajectories is exponential in the size of your state space. This is merely linear in the size of your state space. OK, so we're going to use mu to define this state action marginal, which we'll calculate by calculating the backward messages, calculating the forward messages, multiply them all together, summing over all the states and actions to normalize them, and getting these probabilities. So we can calculate that. And then this bit is simply given by the sum over all of the time steps of the integral over all states and actions of mu ST-AT times the gradient of r at ST-AT. So take every single state, every single action, for all of them, multiply together mu and grad r, and then sum them all up. And that gives you the expression for that expected value. This seems like a lot, but it's still linear in the time horizon, linear in the state space, and linear in the action space. So if you don't like seeing lots of integral signs, you can also express it as a dot product between a vector mu and the whole matrix of grad r's. So anytime you have sum of an integral, you can express that as a dot product. Of course, if your state space is continuous, it's a dot product between infinitely large vectors. So we'll just pretend it's not continuous for now and come back to that later. But if it's discrete, they really are just giant vectors, and you can, in fact, build those giant vectors, multiply them together, and get a solution for this. And this will give you a gradient that you can use if you can enumerate all states and actions. OK, so mu gives you a state visitation probability for each S and A, and the grad R that you can calculate for every S and A. So this basically amounts to saying, let's calculate how often we visit every state and action, and then multiply those probabilities by the gradient of the reward at that point. And that'll give us that second expectation, the first one we get using samples from our demonstrations, take the difference, and then give us a gradient direction. So from this, we get the classic dynamic programming maximum entropy IRL algorithm. This algorithm can be written as follows. Step 1, given a current psi, which you initialize maybe just randomly, compute a backward message beta STAT, just like we did on Wednesday. Step 2, given that same psi, compute a forward message alpha ST, again, the same way that we did in lecture last week. Then compute your mu's by multiplying together the betas and the alphas and normalizing. Then evaluate the gradient by using either the Scary integral or a dot product, which are exactly the same, depending on your tolerance for funny math symbols. And then just take a gradient ascent step on that gradient. So this is basically gradient ascent for learning reward functions. And of course, the worst part of it is calculating these messages and then calculating and normalizing the mu. So if you are blessed with a low-dimensional or tabular state and action space and full knowledge of your transition probabilities, you can calculate those messages exactly using dynamic programming, sum over all the states and actions, and actually calculate this gradient. And in small, discrete state spaces, this actually works, and you can use this to learn reward functions. It actually tends to work quite well. Now, why do we call it maximum entropy? Well, you can actually show that if you follow this procedure, in the case where your reward function is linear in some features, this will actually give you the solution that maximizes the entropy of the resulting policy, pi r psi, subject to the constraint that the feature expectations of that policy are equal to the expert's feature expectations. Which is another way of saying, find me the most random policy you can that still matches the expert. This is desirable for the same reason that maximum entropy models for other machine learning problems are desirable, because it makes the fewest other assumptions. It's saying, other than matching those feature expectations, don't assume anything else about the behavior. Meaning everything else should be as random as can be, other than those feature expectations. And it turns out that that actually makes a lot of sense if you're modeling human behavior, so you're sort of making the fewest additional assumptions. If you have other assumptions, add more features and try to bring them into your problem statement that way. Now this is for a linear reward function. Of course, later on we'll want to do this with nonlinear reward functions where things aren't quite so simple. OK. And this does actually work. So this is the original Maxent inverse RL paper. And in the original Maxent inverse RL paper, they applied this method to problems that were discrete and relatively small, but still had some real-world applicability. So what they did is they took GPS data from taxicab drivers navigating a road network in Pittsburgh. Now, navigating a road network can actually be cast as a discrete tabular MDP, essentially a graph consisting of all the intersections. And then on that graph, you can take your taxicab driver's data, treat that as demonstrations. You can do dynamic programming to calculate visitation frequencies for any navigational policy, and get back a reward function that describes how the taxicab drivers chose to navigate. And you get some interesting results, like how much they prefer major streets versus highways versus local streets, how much they like driving fast, driving slow, etc. And you can actually get a GPS navigation system that drives the way a taxicab driver drives. So that's kind of neat. So even with relatively small discrete state spaces, you can actually get these methods to come up with highly non-trivial solutions. All right. So at this point, I'm going to take a break, and I will come back at 11:02, and then we'll describe how to take these ideas from small tabular state spaces to large and continuous state spaces.
It's run through 34. 340,000 on all three of them.
Oh, wow.
So. Thank God for GPUs.
This is homework 3.
Yeah, but I trained 9 million overnight on the first one because I have a 2080 Max Q.
You shouldn't need 9 million for Pong.
Yeah, but the like it was getting 19.
Oh, I see. You just needed those last 2 points.
Well, no, it was I started it when I went to sleep and I woke up and it had done 9 million.
I see.
Like why would I?
It just stays the same after 4 meetings, right?
Huh?
It just stays almost the same after 4 meetings.
It like slowly inches its way up.
Depends on your hyperparameters.
A little bit. We don't have homeworks like this anymore, do we?
No, the next 2 should be a little quicker.
Good.
I mean, you can still do them on Atari if you want, but the required stuff is not on Atari.
I feel like no one's gonna do the part 3 on Paul.
No.
No. Definitely no.
Why would you?
Like 3
No.
times why? Not even an option.
Like that is a non-optimal decision.
Very unoptimal.
All right, let's continue. So before the break, we saw how we could derive maximum entropy inverse RL algorithms for small tabular state spaces. And now what we'll discuss is how to actually scale up these ideas to the kind of problem settings that we might really want to apply these methods to. So what's been missing so far? So far, maxent inverse RL requires solving for the soft optimal policy in the inner loop. So we have to run that dynamic program to get the beta, to get the alpha. Once we have beta, we basically have a policy. So we're essentially solving the entire RL problem in the inner loop for every single gradient step. It required enumerating all state action tuples to get the visitation frequency for the gradient. And of course, it requires knowing the dynamics. So to apply this in practical problem settings, we're going to need to relax these assumptions. We'll need to handle large and continuous state and action spaces. We'll need to deal with states that are only obtained via sampling, so without having to actually know what P of st plus 1 given SDAT is, just by sampling entire trajectories. And that means that if we can do that, we can handle unknown dynamics. So let's see if we can pull that off. Let's deal with unknown dynamics in large state action spaces. So let's assume that we don't know the dynamics, but we can sample, just like in standard model free RL. Remember that our gradient is given by this equation. It's the expected value of the derivative of r under pi star minus the expected value under the soft optimal policy for our current reward r psi. That's what this p tau given O1 through t comma psi represents. So the first part, of course, as you all remember, is easy. That we just estimate using our demonstrations. So it's the second part that is difficult because it requires taking an expectation under the soft optimal policy for the current reward function. So we could devise a decently well-defined but highly impractical algorithm, which is learn that entire soft optimal policy using any maximum entropy RL algorithm. So you could, for example, use the soft Q-learning stuff that we discussed from last week, or that version of policy gradient that has the entropy term. Any of those will work. The problem is that you have to run them to convergence for every single gradient step that you take on psi. But they don't require knowing the dynamics, and they don't require enumerating the state action space. Of course, as you probably realize from homework 3, running RL to convergence takes a very long time, so you have to do that every single time you take a gradient step. Then you're going to be waiting for quite a while. So we don't really want to do this, but if we had to, I guess we could. So what we're going to do is we're going to try to approximate it so we don't have to run RL to convergence in the inner loop. So, but if we have to, this is our RL objective, the maxent RL objective. You can do like policy gradient on this or something like that, get back a policy, take samples, and estimate this using samples. Okay. So let's think about more efficient sample-based updates. So somehow we need to obtain some samples here for that second term. Ideally, those would come from the soft optimal policy, the maxent optimal policy for the current reward. So we could learn it using any maxent RL algorithm and then run this policy to sample these tau j samples over here. But what if we do kind of more of a lazy optimization approach? What if instead of actually learning that maxent RL policy, what if we just improve it relative to a previous policy? So maybe we had some policy already. We're going to update our reward function and then update our policy a little bit to make it a little bit better with respect to that new reward function, but not actually train it all the way to convergence. So one way we could update it to be a little bit better is we could take, for example, one policy gradient step. Can that actually work? Well, it's not going to give us samples from exactly the distribution we need. It's not going to give us samples from our p of tau given O1 through t comma psi, but it will give us samples from some other distribution. And as we take more and more gradient steps, those samples will get closer and closer to the samples we want. So if we have samples from a distribution that's not quite the right one, but it's kind of close, what can we do? What can we do to convert samples from one distribution into samples from another distribution? Something we've seen before in a previous lecture.
Importance sampling.
Importance sampling, yeah. So importance sampling gives us a tool that we can use to turn samples from one distribution to samples from another. So that's what we're going to do. We're going to improve the policy only a little. Our estimator is now biased because it comes from the wrong distribution. So one solution is to use importance sampling. So now we will calculate our gradient just like we did up there, only now we'll weight each of these samples by a weight wj, and we'll divide by the sum of weights, so the weights sum to 1. And the wj's will be given by the ratio of the probability of the trajectory under the distribution we want. And what we want is p of tau times exponential r psi of tau, divided by the distribution we've got, which is pi of tau. So let's talk about these importance weights a little bit more. We can expand them into our familiar trajectory probabilities. So as we've probably seen many times by now, trajectory probabilities are basically a big product of the initial state, all the transition probabilities, and in the case of your policy, the policy term; in the case of your desired distribution, the exponentiated reward term. So when we take the ratio of these big products, of course, most of those probabilities cancel out because both your current policy and your desired distribution have the same initial state distribution, the same transition probabilities, and all that's left is the exponentiated reward divided by the probabilities of the actions. And that's very, very nice because it means that we don't have to know the probabilities of the transitions. So then our importance weights just become the exponentiated sum of rewards along the trajectory divided by the product of the probabilities of the actions along that trajectory. That denominator can be quite tough to deal with, but at least this gives us a way to get started. So now now you can actually take these ratios, you can plug them in as your probabilities W, or sorry, as your weights W. This gives you an estimate of your gradient that you can use, and perhaps most importantly here, as you're doing these lazy updates to your policy, each of those updates improves the expected reward of your policy with respect to r psi, bringing it closer to the distribution that you're reweighting to. So although importance sampling can be very ill-behaved for long horizons, for high-dimensional spaces, you're actually explicitly optimizing your policy pi to bring it closer and closer to the numerator. So as your policy pi gets better and better, this ratio will actually become closer and closer to 1. So while ordinarily using importance sampling for things that are very far off policy would be a bad idea, here your policy is being explicitly optimized to bring it closer and closer to the distribution that you're reweighting to. So you might suppose that if your policy optimizer is doing a good job, eventually those importance weights will not be ill-behaved, and you'll actually get something decent. And of course you can use, if you so choose, you can use some heuristics to say, well, if my importance weights are too peaked, they're too far from 1, maybe I'll run my policy optimizer a little bit longer to let it catch up with my reward function before continuing the gradient ascent steps on psi. So this actually gives you an algorithm that you can implement that does not require running the policy optimization to convergence every single step. So the first method that actually instantiated this algorithm in a practical deep inverse RL method is a method called guided cost learning, which actually uses guided policy search as the inner policy optimizer, but you could use any policy optimizer you want. The overall structure of this algorithm looks like this. You have some initial policy pi, maybe initialized randomly. You have your demonstrations. Then you generate some samples from your policy pi. This is basically, if you have like a robot, you run the robot. And then you update your reward using the samples and the demonstrations via that importance sampling estimator for the inverse RL gradient. And then you go and update your policy pi to be a little bit better with respect to your reward R psi. So at the end, you get a reward, and you actually get a policy. So the reward is updated according to the difference between the expected gradient of the reward under the demonstrations minus this importance-weighted estimate of the expected gradient under the policy. And this thing actually works. You could have some demonstrations for a person showing a robot how to pour a cup of, in this case, almonds. And then the robot will observe those demonstrations, figure out that the goal is to really pour into this yellow cup, and then pour into the yellow cup at new locations. So the thing basically works. But what we're more interested in at this point is to better understand the structure. So this algorithm can be interpreted as a gradient descent algorithm on psi, on the log likelihood of your demonstrated trajectories. But it also has kind of an interesting flavor to it, because the reward is trying to be a better reward with respect to the likelihood. The policy pi is trying to become a better policy with respect to that reward. And they're kind of competing with each other, because when the reward is updated, it actually drives down the reward for the policy, and it drives up the reward for the expert. When the policy is updated, it tries to, in some sense, do the opposite. It tries to make its own reward big. So it almost looks like they're competing with each other. It almost looks like some kind of a game. And in fact, it is a kind of a game. So the initial policy, you get samples from that policy. The demonstrations, you get samples from the optimal policy. Then you modify your reward according to this gradient, which makes the samples from your policy have lower reward, especially if they're close to the optimal policy for R psi, and samples from the expert have higher reward. So demos are made more likely, samples less likely, and then the policy gets to go, and the policy changes to make it harder to distinguish those policy samples from the expert samples by raising its own reward. So the policy says, you're going to try to distinguish me from the expert by seeing if my reward is low, well, I'll just make my reward higher, and then you won't be able to tell the difference. And of course, once this whole thing converges, you actually can't tell the difference. Once the whole thing converges, the whole point is for the policy pi to look indistinguishable from the expert. So in some sense, it's a game where they're competing, where the only way for them to be at an equilibrium is to actually solve the inverse RL problem. This is an idea that has actually been around for a couple of years prior to the development of this method, but not in the world of inverse reinforcement learning, but rather in the world of generative models. So this was around 2014 or so, there was a paper called Generative Adversarial Networks that came out that proposed an adversarial game of this flavor, not for generating behavior, but for generating pictures. And since then, it's been applied in many, many different places. For example, for turning horses into zebras, for generating faces, for turning hand-drawn pictures into cats, and vice versa. If you want to play with this, look up Pix2Pix. It's a lot of fun. You can draw a loaf of bread and then turn it into a bread-shaped cat. It's really awesome. And underneath all that, there's an adversarial game. And that adversarial game involves a competition. And it's, in a sense, a competition between a sort of policy and a sort of reward function, only we call them something else. We call them a generator. That basically plays the role of the policy. And the generator takes in some random noise and outputs a picture. And initially, our generator is very bad, and it outputs bad pictures. And those are our samples. And then it has data. Those serve the role of demonstrations. And we assume we have samples from the optimal data distribution, the optimal data expert, who draws good pictures of zebras, or good pictures of faces, or good pictures of cats. And then the game proceeds as follows. The reward function is now called a discriminator, and its job is to distinguish whether a given picture came from the data or from the generator. And it's trained in a fairly obvious way. It's trained to be a binary classifier that assigns positive labels to the data and negative labels to the samples from the generator. So if d psi of x is the probability of x coming from the data, then you want to maximize log d psi of x for all the samples from the data, and then maximize the log of the other label, 1 minus d psi of x, for samples from the generator. And then the generator does exactly what you expect. The generator gets to go, and the generator tries to produce pictures that the discriminator thinks come from the data. So before, we had a reward function that was trying to give big rewards to data and small rewards to samples from the policy. Now we have a discriminator that tries to give positive labels to data, negative labels to samples from the generator, and a generator that's trying to maximize the probability of being real. In fact, this similarity is not just superficial, it can actually be made exact. So inverse reinforcement learning can actually be interpreted as a generative adversarial network where we have a particular choice for the discriminator. And in particular, the discriminator needs to contain a reward function inside of it. So here's how we can interpret inverse RL as a GAN. Which discriminator is best in a GAN? So if we got to pick any discriminator, well, the optimal discriminator can be shown to obey this equation. So if you could choose any discriminator you wanted, and you knew the true density under the data, p star of x, and the true density under the generator, p theta of x, then the optimal discriminator would be p star of x divided by p theta of x plus p star of x. That makes a lot of sense. So for a given image, its probability of coming from the data is like 0.9, and its probability of coming from the generator is 0.1, then you want to say it's 90% likely to come from the data. So in inverse RL, your goal is to get that optimal policy to approach p tau times the exponential of r tau. So we're going to choose this parameterization for our discriminator in order to recover inverse RL. We're going to represent our discriminator as this ratio, and we'll just plug in for p star our p tau times exponential r, and then for p theta, we'll just keep it as p theta. Now, what we're going to do from here, of course, is we'll plug in the definition for these distributions, and because they're both coming from some policies, just like before, all the transition probabilities will cancel, all the initial state probabilities will cancel, and we'll actually recover something very convenient. So the p taus represent the p of s1 times the product of p of st plus 1, etc. All the transition and initial state terms. Once they all cancel, we're left with a very convenient expression for the optimal discriminator. It's the exponential of the reward divided by the product of all the actions plus the exponential of the reward. And the only pesky detail is that you do have to normalize this thing. And we saw before that normalization is actually a really big pain. So we'll come back to that shortly. But for now, we've rewritten our optimal discriminator in this form. Now, there's a little detail that I should mention here. When we talk about generative adversarial networks, the kind that generate pictures of zebras and faces, we almost never actually want to do this, because for regular generative adversarial networks, it's not just that we don't know p star, we actually don't know p theta. So in a regular generative adversarial network, the generator takes in some noise and outputs an image, and actually calculating the log probability of that image is very, very hard, because you might have multiple different noise samples leading to very similar images. But in reinforcement learning, this is no longer the case, because in reinforcement learning, the transition probabilities here cancel, and all we're left with is these action probabilities, which we do know. So this actually allows us to write out an expression like this, which would not be possible for regular generative adversarial networks. OK, so now what we're going to do is we're going to optimize this discriminator with respect to psi. I won't go through this derivation in detail on this slide, but if you actually write out exactly the discriminator objective from before and plug in this definition for the discriminator, if you crunch through it, you'll actually recover an expression for a gradient that matches the gradient for inverse RL. And you can do this at home. Everything here is algebra. You have the log of this, plug that in there, work through it, and you will end up with an expectation under the data of grad R minus an expectation under the policy of grad R. And it's kind of cool that you get that just by optimizing the classification accuracy of a discriminator formed via the ratio of the reward and the reward plus the policy. So not only does it appear as though you're training the reward to make the demonstrations distinguishable from the samples. In fact, you can literally train it that way. You can actually create a classifier out of the reward function, train that classifier for maximum accuracy via the same expression as in generative adversarial networks, and you will actually follow the same gradient as the IRL gradient. In fact, it actually gets better. Not only will you get the right gradient, you can in fact optimize z with respect to that same objective, and somewhat surprisingly, you'll actually get the right z. And that is very, very nice, because this z was basically the bane of our existence before. Figuring out that z required us to sample these trajectories or calculate visitation frequencies, all this other stuff. Now we have a much simpler answer. Just optimize z with respect to the same objective as your size. And this paper actually shows why that gives you the right z. So we have a very simple algorithm now. Just optimize the thing as a binary classifier. So the way that inverse RL interpreted as a generative adversarial network works is that you have your generator, which is your policy, pi theta of tau, and you get samples from that. You have your data or your demonstrations, and you get samples from that. You train your discriminator with a maximum likelihood objective, maximize the log probability of assigning a true label to data and a false label to samples, where the discriminator has that special representation as a ratio of exponential R terms divided by exponential R plus the product of policy probabilities. So it has this special term, this special form, and psi affects these R terms only. And then you train your policy, and you train your policy to make it harder to distinguish from the demos. And you can also show that actually the generator objective matches the policy objective, so you just climb the gradient on the rewards. And this gives you an inverse RL algorithm. And you can actually show that at convergence it'll match the probability distribution, so pi theta and p star of tau will match, and you get the right reward function. So this is described in detail in this paper. A practical algorithm you can derive for this is something called adversarial inverse reinforcement learning, described in this paper. And you can do like fun things, like for example, give a demo of a little ant. This is just like the ant you had in homework 1, only it has angry eyes now, to emphasize the fact that this is inverse reinforcement learning. And then you could, for example, learn a reward function from the regular healthy ant, and then take that reward function and then modify the system to break 2 of its legs, and then optimize the learned reward function and get a behavior that actually causes the broken leg ant to walk. So if you recover the right reward function, you can actually transfer it to new situations and get some decent behavior. All right. Now, the last thing the last algorithm I want to cover is actually, it actually predates adversarial inverse RL, but I'm covering this third just so that there's a logical progression, which is actually kind of a simpler method. It doesn't bother learning reward functions. It just takes this generative adversarial network analogy very, very literally. So just like before, we're going to have a policy and we're going to have data. But now, when we train our discriminator, we're not going to bother with that special representation that contains the reward function inside of it. We'll just directly parameterize d psi as a binary classifier, as a neural net representing a binary classifier. And then we won't get a reward function explicitly out of this, but it turns out that you can actually recover an objective for RL out of it by taking the log of d. So you essentially change the policy to make it harder to distinguish from the data. You do end up with a policy that matches the distribution of the data, but you do not actually get the right reward function out of this. So at convergence, you can't actually use log d as a reward, and it's easy to see why. Once everything is converged, log d will just output 0.5 everywhere, right? Once you can tell the demos from the data. But you will get the right policy. So this can often be simpler to set up. There are fewer moving parts. There's no funny ratio thing. There's only a binary discriminator. But the discriminator doesn't know anything at convergence. Only the policy does. So if what you care about is really the policy that you get by matching the intent of the expert, this will give you that. If you care about what the intent actually is, it won't. So the way this looks is you have guided cost learning. Guided cost learning takes the, essentially the samples from the policy and the human demonstrations, and it tries to minimize the reward of the samples from the policy and maximize the reward of the demonstrations. And it learns the distribution that matches the exponential R. The method that just uses a regular discriminator is called generative adversarial imitation learning. Very similar deal, takes in policy samples and demonstrations, and it has a classifier that tries to make the samples look as false as possible and the demos look as true as possible, where d of tau is basically the probability that tau is a demo. And then you use log d as the reward. So they're basically the same thing, just with different representations for d. So over here, the d is represented with this ratio. Over here, it's just represented as a binary classifier. You can use both of them to get some pretty neat results. These are some results from a paper by Hausman, Chabatar, Schall, Saabme, and Lim that shows extracting multiple different behaviors from demonstrations. So you get demonstrations that show this humanoid running in different directions, and it actually tries to perform simultaneously both reward extraction and clustering to cluster into different groups. This is a paper by Peng et al. Showing some motions learned via this method over here, the generative adversarial imitation learning method, from motion capture of humans doing acrobatics. So the video on the right shows a policy learned from the motion capture on the left. So you can do some pretty fun stuff with this. If you want to read more about inverse RL, here are the classic papers. The first one describes the maximum margin method that I covered at the very beginning. The second one is the paper that proposed the maximum entropy inverse reinforcement learning framework with the taxi cab driving. And here are some more modern papers, guided cost learning, generative adversarial imitation learning, and the adversarial inverse RL paper. This is also a paper that did inverse RL with deep neural networks right around the same time. So if you're interested in this kind of work, check out these papers. All right, so at this point, I'm about out of time. If any of you have questions, feel free to come to me after lecture, and I'll see you all on Wednesday for transfer learning.